So today we're going to talk about synthesis. Synthesis is this idea that a molecule can be more complicated than we could possibly get to in one step, right? So as organic chemists, we make these really complicated molecules, and oftentimes the starting materials we buy have to be cheap and readily available, which means that we have to do a lot of things to them to get them to a more complicated product. So we're just getting into synthesis, and there are really two big patterns that we might be seeing early on in some of our synthetic routes. So the first pattern I want you guys to see is, let's say we have a heteroatom X on this carbon, and we wanted to move it to this carbon. The way that we can do that is essentially thinking of additions and eliminations as inverses of each other, right? If I eliminate X, I can then add it somewhere else. Or I could add Y somewhere else. I can add something else, right? If you think of this as pegs on a pegboard, if I wanted to move X to this location, to the second location, I would have to eliminate it first and then add it into the second spot, right? So the first step to moving this is eliminating it. So in order to do that, X must be a leaving group. So X must equal some kind of leaving group. And I can use some kind of base. What base you use depends on the molecule you're working with, what your goal is. But here it doesn't really matter. We could use NaOH or even a bulky base like potassium terbutoxide, and we can get this elimination product. Once we have the elimination product, we can do an addition. In this case, since we're going to be adding it to the less substituted part of the double bond, this needs to be anti-Markovnikov. So the way that we can add it, halogen HX, like let's say this is chlorine, anti-Markovnikov, is by adding um, H2O2, adding peroxides. That enables us to get the anti-Markovnikov addition, whereas just HCl would add here. So relatively straightforward steps, but it's a pattern you're going to have to see a couple of times to make sense. So if we want to move where our functional group is, we have to first eliminate it and then add it specifically to the carbon that we want to add it to. So let's try an example of this. So take a minute and see if you can kind of replicate this on a pretty direct example here. All right. So I mean, if you notice, this is almost the exact example, right? We had uh, our X, which is just our um, non-carbon thing, our heteroatom, is right here on this carbon. We want to move it to this carbon. So the first thing is we have to eliminate it. We're going to do that with some kind of base. In this case, it doesn't matter. It's a secondary, so and if I eliminated from either side, it would be the same molecule. So I'm just going to use sodium hydroxide. That's going to give me this elimination product. And then I want to add antimicrobnicov, so I'll use HCl and peroxides. That'll reliably get me this product. So in two steps, I was able to move my bromine to the secondary on the secondary carbon to a chlorine on the primary carbon. All right, let's see if we can do it backwards. How would we try to do this backwards? Take a second. All right, in this case, we're doing the same thing. We have to do an elimination, so we need a base. One tricky thing about this one is this is a primary alkyl halide, which prefers substitution. So we ideally, if we use sodium hydroxide, we'd risk doing a substitution here, which we don't want to do. So I'm going to just use a really bulky base. So my default bulky base is KOTBU. That's the better option. If you put sodium hydroxide here, um, we'd be a little bit lenient with the grading, but K the bulky base would be better for this case because it's a primary alkyl halide. You don't want to do a substitution. So that would get me an elimination product. Then we're adding this bromine. We want to add this bromine Markovnikov, not anti-Markovnikov. So I can just use HBr. I don't need the peroxides. The peroxides put it anti-Markovnikov. HPR puts it Markovnikov. All right. So here's a little bit of a trick. This time, OH is not a leaving group. So I can't do an elimination on an OH because it's not a leaving group. So I need to first turn OH into a leaving group. See if you can do it. All right. So for this, we have a lot of options. There's a lot of different things we could do. We just need to turn this OH into a leaving group. So list some ways that we could turn OH into a leaving group.
Using an acid.
So if I used an acid, it could turn it into a leaving group, but I risk doing some sort of substitution. Like if you used HCl, it would probably substitute. Although H2SO4 and heat, which isn't something we talked about, but that will do an elimination. So that is an option. I'm not going to test you on this reaction, but that is a very convenient way to go from an OH to an eliminated product. But we haven't talked about that one, but feel free to use it. What's another way we could turn OH into a leaving group?
Can you do H3O plus?
So HCO plus would protonate the alcohol, and then it would just replace it with another alcohol.
Can you do NaH?
So NaH, a base. So the problem with NaH is OH isn't a good leaving group. You can't do an elimination on it. Can I turn OH into a leaving group? So my first thought is I could use, SOCl2. That would just straight up turn it into that. Or I could use PBr, turn it into a bromine. It does not matter. Another one would be TS chloride, which would turn this into tosylate. All of these work. It does not matter. I just need to turn it into a leaving group so I can do an elimination. So I would just find your favorite way to do it. It could be PBr3, it could be SOCl2, it could be tolusyl chloride. Does not matter. Or you could use the H2SO4 and heat. That also works. Then I need to add I anti-Markovnikov, so I'm going to go HI H2O2.
Dr. Little, could you please repeat how to know which base to use, like between NaOH or one of the bulky bases?
Okay, so um, we'll talk about that more in a second, but that's a good question. We're getting to that. All right, here, another similar problem. So this one, we need we need to do an elimination. We need to eliminate our bromine. So I'm going to use sodium hydroxide because all things being equal, we're going to form the more stable double bond, right? So we're going to eliminate this hydrogen. You guys don't need to show the curved arrows. I'm just illustrating it here. Then just to go here, it's just HCl. It's the Markovnikov addition adding to the more substituted part of the double bond, my chlorine. So this is a different problem, right? If I formed that same double bond with NaOH, I would run into issues. So how do I get around that problem? How do I avoid making this double bond to make a double bond that would help me make this product instead?
Do you have to use a bulky base? Because it
Right.
can't fit.
Right. Notice the difference is one of these hydrogens is in a really bulky spot and the other one's not. So if I want to avoid going to the bulky hydrogen, I can use a bulky base, which KOTP is my go-to. You can use DBU, LDA, really anything I listed as like a bulky base at the beginning of class. But just find one you like and use it. And this one, the KOTB would not be able to get into this bulky spot, so it takes this proton, so I get that elimination product. Which is helpful, right? Because I want to add this bromine all the way over here. So making the double bond on the left wouldn't have been helpful. I want to make it to the right of that leaving group. Then how do I add bromine anti-Markovnikov?
HBr and then H2SO2.
H2O2. It's hydrogen peroxide. See, these seem complicated, but you start to see the same reactions over and over and over. And honestly, it's a way to kind of practice the reactions too. So the more you do this, the more like you become comfortable with these reactions. So this is a tricky one. I'll give you guys a minute to work on this one because this one requires a little bit more time. All right. So the first thing we need to do is OH isn't a leaving group. So we need to make it into a leaving group. I'll use PBr3 this time just to mix it up, but it does not matter as long as you made it into a leaving group, either a halogen or a tosylate. Then if I eliminate it, I want to use sodium hydroxide to make the more substituted double bond, right? Potassium terbutoxide would substitute, make a double bond here, which is not what I want. Is this going to get me, can I use this to make HBr directly? No, it's not, right? Neither one of these carbons is touching HBr and no rearrangement is going to get me there. So I need to do another addition. I'm adding to the less substituted double bond, so that's anti-Markovnikov. I need my peroxides. And then I need to eliminate one more time. All right, so I can get a double bond and move this bromine one carbon out further. Am I going to use sodium hydroxide or potassium terbutoxide? And why? Do I want to make the more stable double bond or the less substituted double bond?
You're gonna do the potassium terp. I can't even say it.
Yep. No, you're close. Potassium terbutoxide, right? Then I can use that. Oh, that's the ugliest arrow I think I've ever drawn. HBr H2O2. All right, I'll give you guys a second to write that down, but right, so that the idea here is that we eliminate it, but that didn't get us far enough, so we had to keep going. We had to keep adding and eliminating till we get our bromine to the right spot. I mean, this is a little bit of a ridiculous example, but okay. A couple of questions here. That are good questions. On the exam, will we need to draw mechanisms for addition reactions? No. Unless I ask specifically for a mechanism, you do not have to include the mechanism. I do want you to think about it. I think it's important, but like for something like this, if you drew a mechanism out for each one of these reactions, it would get really complicated really fast. We're just showing the steps to go from starting material to final product, the different reactions. The mechanisms are kind of implied in there. Could I use potassium tert-butoxide here? No, because potassium tert-butoxide would give me that product, which doesn't help me, right? It would make the less substituted double bond. So that wouldn't be good. Right? That wouldn't help me get my bromine where I want it to go. BH3, sodium hydroxide, H2O2 is only used when you want to add an OH, and we will get to that. So every time we want to move a carbon to another carbon from more substitute to less substitute, we have to do elimination. Every time you want to move a substituent from one place to another, you're going to have to eliminate it and re-add it. So yes, you're going to have to do an elimination and then an addition. You're not moving carbons around, you're moving the thing on the carbon. The 3 arrows does not mean you need 3 reactions. It just means that multiple reactions are going to be needed. Sometimes you won't even see people do the 3 arrows. I just do it to really emphasize that this is a different kind of question. We're doing something else. This is not going to just be one reaction. But the number of the arrows there is not indicative necessarily that we need to do 3 reactions. All right, moving on. All right, so the second and kind of final major pattern you're going to see is the formation of ethers. Ethers are ROR, so this is an ether, right? It's a oxygen with carbons on either side, right? It's different from an alcohol. We have a different name because it reacts differently. It's a different thing. So, if you just think about this reaction being some substitution in SN2, and you have sodium hydride as your base to remove this hydrogen. So you could use any non-nucleophilic base, any base that's not you're not worried about adding, like that's never going to happen with sodium hydride. So it's a safe base to use for these reactions, right? If you think about one of the problems with bases is that they look and act like nucleophiles a lot of times, but sodium hydride in particular just won't. It's a very bad nucleophile. It only acts as a base. So this, takes the hydrogen and you do the SN2. So we've used additions, we've used eliminations. This is how we can use a substitution to be a part of our total synthesis. So you'll form these ethers. And here I'm going to kind of introduce a new stipulation. I don't want you using anything that adds carbon outside of what I give you as starting material. So I'm given this, which has 1, 2, 3 carbons, and then my final product has 1, 2, 3, 4, 5, 6. So that means I'm going to have to use this starting material twice. I'm going to have to do 2 different things with it. So let's imagine X being some kind of leaving group. We can keep part of our stock of that starting material as what it is because that's useful for us. And then we'll turn the other one into an alcohol. Um, in this case, using sodium hydroxide because sodium hydroxide will do a substitution on a primary leaving group, which is what we have. Um, so I do want to make sure we're trying to do substitutions on primary leaving groups. As soon as it becomes secondary, you're going to get probably more elimination than substitution. So we're going to keep our leaving groups primary, and we've got to make one part of it the electrophile, and we've got to turn the other part of it into our alcohol, the nucleophile. See if you can do it on your own. So this example is almost exactly the same example from that I gave you in the starting material or in the example, right? This already has a leaving group where I want it to be, so it's good. Then I need to turn another version of it into an alcohol nucleophile, right? The sodium hydroxide. Again, you don't need to show the mechanisms, but it's just going to do a substitution on that primary leaving group, and I'm going to get this. Then if I add them together with a little bit of base in there, I can get my final product. All right, so for the second one, the roles have flipped, right? I have my oxygen nucleophile, I have my alcohol, but what I don't have is my electrophile. I don't have my thing with a leaving group. So I'm going to keep the alcohol the same. Then to another version of it, to a different portion of it, I need to turn it into some sort of leaving group. So I'll just I'll use PBr3. You could use HCl, you could use SOCl2, anything that would replace that alcohol with a leaving group. You could do TS chloride. But if I add them together with sodium hydride, I can get to that product. See if you can do this one. Someone said, no matter what the case is, I can always use PBr3 to turn my OH into a leaving group. Yes, that's a safe bet. PBr3, SOCl2, whatever you want to use. They all work to turn an OH into a leaving group. Someone else said, I don't understand. How are they adding together? Can you explain that again, please? Well, let's look at this reaction. If I gave you this on a test, what would we expect the product to be? We have a base, we have what looks to be a nucleophile, we have what looks to be a primary alkyl halide, right? So in this case, my base will deprotonate my alcohol, giving me a charged alcohol, which then will do a substitution on this alkyl halide to give me this. Right? So I'm just saying I need to make this product. So I need an alcohol, which is going to be one half of it, and the leaving group, which will be the other half of it. Right? I need a nucleophile and electrophile to pair together that look like this final product. And in this case, it's the oxygen binding to the carbon with the leaving group. That's a good question. I think that's honestly the hardest thing to see about these. We've almost skipped a step. Like, I'm expecting that you can kind of start to see these SN2s a little bit more easily. So for this guy, this reaction, OTS, well, that's a leaving group. So I already have a leaving group here. Um, so that means I can keep one form of it. And I need to substitute that out with another equivalent, another version of itself. So that's my electrophile. I need a nucleophilic version. So I'm going to, what could I use to substitute that tosylate out for a nucleophile? Something that could be nucleophilic for the substitution. I can use sodium hydroxide. Sodium hydroxide is going to substitute that tosylate out for an OH. That gets me this. And these two things together, right? If this alcohol were to then substitute that, I would get to that final product. On the surface, this looks more complicated, but it's the same question. I've just added a benzene ring to it.
What does the NaH do at the end?
It's just a base. It's just a non-nucleophilic base. It removes this, like if we look at this mechanism here, the NaH is used to remove the proton off the oxygen so we can do an SN2.
I have a question. Why can't, like, how do we know when we can just like make water to make the hydrogen go away, or when we should use the NaH to get the hydrogen out of there?
For these, it doesn't hurt to add a base. If you did this without adding NaH, we'll still probably give you credit. I'm not going to be upset. I'm just trying to be as correct as possible. If I were to do this in a real lab, I'd use a strong base so I can get a charged nucleophile so I can do an SN2.
Okay, but it's like the same concept of just like making a water molecule, right?
What do you mean?
Like, you know how sometimes we just make a water molecule if like the oxygen has too many bonds and we take away the hydrogen?
Yeah,
So the
you're technically not making the water molecule in those cases. Those are done because the reaction's done in water. But no, this is a little different. So sodium hydride is a strong base. It's going to actually catalyze this reaction. It's going to get it to go, right? It's going to deprotonate that hydrogen first because it's charged. It's really strong. Whereas what you're talking about is like at the end of a mechanism, when something has a positive charge, we can use neutral water to neutralize it. But like water in this case would actually not help us very much because it could be nucleophilic.
Oh, okay, thank you.
And yeah, you might get a substitution. So I use a non-nucleophilic base. That's why we have that term, right? It enables us to remove a proton without worrying about it. But in the sense that you're removing a proton in both senses, yes, they both act as bases, but this one is a base we're adding on purpose. Right. So the only thing that's really left is combining these ideas. So notice this product wouldn't flow from these starting materials. Why? Why would these starting materials not get this product?
Is it because the formation on the right is different?
Yeah, if you look at this, if this were to add in here, I would get this. Is this the same thing as this? Are these the same thing? No, they're different molecules, right? So sometimes, if I have a specific product in mind, it means I have to change my alkyl halide, I have to change my alcohol to get them in the right formation to do the right substitution, right? So here's what that would look like, right? I want the alcohol, instead of looking like this, or sorry, right? When it adds into the alkyl halide, I'd rather it looks like this. That way I can get this piece, right? So this goes back to, in order to go from here to here, I've got to change the location of that OH, right? It's no longer on the end carbon, it's now on the middle carbon. So this is the first idea with our new idea. So here in this example, I've eliminated that leaving group using a bulky base because it's a primary leaving group to get me this. So if we remember, when do we use bulky bases? It's either when we have a primary leaving group or we want to make the less substituted double bond. That's when we use a bulky base. That's a little summary of when to use a bulky base. Then I wanted to do the Markovnikov addition of an OH, which is this beast of reaction conditions, to give me this OH, which is what I wanted. I wanted the OH on the middle carbon. And then that can do a substitution on this, right? To get this product. So this is where working backwards can be helpful. So if I look at this molecule, I say a substitution with an alcohol and a leaving group creates an ether, right? It creates this. So one way we think about it is through disconnections, right? So I'm forming a bond in a reaction. What bond did I form to get this product? So when I look at this, I see I've probably made that disconnection, right? I had this alcohol and this leaving group, and I did this, right? I imagine I've got this piece and this piece. One needs to be the nucleophile, one side needs to be the electrophile, and then I add them together. And if I have a preference, I'm going to put the electrophile on the primary one so I can do the substitution. I'm going to put the halogen on the primary one. So the first thing I would do is look at my product and say, all right, what two pieces got here, right? I'm going to look at the heteroatom. I'm going to look at the oxygen. I'm going to say I either cut it here and got this, or I cut it here and got this. Right, I have two options. Which one seems like it'd be more likely to do a substitution? Top or bottom?
The bottom, because the leading group's on primary.
Yep, the bottom. So I'm going to use, I'm going to imagine that I've made this cut. Right? This bond is the bond that I want to disconnect, so I'm going to cut it. I'm going to imagine that one side was my nucleophile, the other side was my electrophile. Do you guys see that? Is that visible? So once I have this, then I need to plan using my starting material. How do I get here? So I see that I already have a leaving group on the end carbon. So I already have this. That's a check. I've done that. Then now I just need to make this, which I don't have. The question is, oops, can you turn the starting material into that alcohol? So I need to change locations of it, right? Here it's on the end, and I want to move it to the middle. So what do I have to do? Nothing. Since it's a primary leaving group, I'm going to use a bulky base to do an elimination. Then do I know a reaction? Oh, I don't want to use a curved arrow. Then do I know a reaction to get there?
The mercury one.
Yeah, the mercury one, the Markovnikov addition. So now I have both my pieces, right? This plus this with sodium hydride gets me my product. right? My nucleophile plus my electrophile with a base will get me to my product. So this is where the thinking backwards for a little bit helps, right? What is the major disconnection I make? What are the pieces I need to be striving to make? And then we can put them together and make the final product. So I'm gonna zoom out so you can see the next one. So someone asked for the last question, could I have used sodium hydroxide instead of potassium terbutoxide? Ideally, you need a really bulky base because a primary alkyl halides favors substitution over elimination. So we need a really bulky base to make up for it. It's one of those things where if you got everything else right on a test, I'd be like, we'd be pretty lenient. You'd probably get 9 out of 10 here. But for a perfect score, let's use the right base. But to be honest, this is more about seeing if you guys can plan ahead, see if you guys can see these patterns and start to apply them to a synthesis. Start to use these reactions in a reliable way. So if you get a little thing wrong here and there, it's not going to kill you, right? There's going to be a lot of, we're going to be very generous with partial credit on this one because there's going to be a lot of people who probably just don't put any answer. So let's, as long as what you're putting kind of makes sense to us, we can be generous with the partial credit. But potassium terbutoxide is the better base here. So here I see my ether and I see that there's 1, 2, 3 carbons and there's 6 here. So I know that I either need to cut here or here. Do I want the alcohol? If I cut here, my leaving group would be secondary. If I cut here, my leaving group would be primary. So I'm going to do this. Do you guys agree? Were you able to get this as targets? We've got to make these now. So now my focus turns to making these. I already have this one, right? That was the starting material I was given. That was nice. Now I need to make this one. So this OH is in the wrong place. I need it on the end. So that means I need to do what? I need to do an elimination. But in order to do elimination, I need to turn this into a leaving group. Now I can do elimination. It's a secondary. Both sides are the same. It does not matter what base I use. I'll just use sodium hydroxide. I get this. Then I need to do an anti-Markovnikov addition for a leaving group. Again, it doesn't matter. I can use HBr, H2O2 to get here, which matches the description of what I was going for. So now I still have this starting material. I can add this. I can add these together with some base, and I get my product. Were you guys able to get that? If you weren't, where did you get stuck?
I keep like not drawing the part where you cut it in half. And then I just made BR, or I used PBR3, but I like put it on the wrong, like I had the leaving group on the wrong spot because I didn't do that first part. That makes sense.
Okay, yeah, it's important. It's important to figure out what are my targets? What am I trying to get to, right? Otherwise, yeah, things might get messy. You don't want to make the wrong product. So, you guys work on the next one. If anybody else wants to speak up and say what you messed up on, um, it might be useful to other people or people who are watching this video because they might have messed up the same thing. Nothing. You guys all got perfect.
I like tried skipping the thing. I didn't do PBR3. I just tried doing like NaOH first. I just forgot to do that.
Yeah, that would just deprotonate the alcohol. It wouldn't do the elimination we want to do. Again, if you like then drew, it's one of those things where like if you did sodium hydroxide there and then drew the elimination product, we'd take off a few points, but if everything else was right, we'd give you credit. Like you can think about each one of these pieces being like 2 out of 10 points. So if you miss the reagent in the product, that might be, a couple points, 3 points.
Can you just show again how you choose your targets, or like how you would cut this to find your thing?
Okay, yeah. So remember very early on, I said our eyes go to heteroatoms. So I look at our product and I say, well, there's my heteroatom. I made a bond with an oxygen. I need to make a bond with an oxygen and a carbon, right? That's what we're doing with these substitutions. So if I need to make a bond with an oxygen or carbon, I can either make this oxygen carbon bond, or I can make this oxygen carbon bond, right? If I imagine where like the side with the oxygen is an alcohol and the other side is the leaving group, right? It leaves, it's gone. So, do I want to cut bond A or bond B? What would be the more reasonable thing to cut?
Would it be the first one or
It,
A?
it'd be A. Why?
It it looks most like the reactant is really what I thought, but I don't really know.
Well, it does look like the reactant. But it's because whatever is on the oxygen side, right? So if we cut it on A, we're gonna have to do this reaction. Like A is saying that we're gonna do this reaction. Where this is A, where B looks like this. Right? So the only difference is what side is my nucleophile and what side is my electrophile. Right? We know one side's got the leaving group and one side's got the alcohol. We can cut it either way. What side seems more reasonable for a substitution? I lost you.
Oh, is it because the leaving group is on the primary?
Yep. I
Or
like A a lot better than B. Although if you did B and did a correct synthesis up to B, you're going to get partial credit. You're going to get some credit, right? But I like A because it makes a primary leaving group. That's an advantage to me. All right. So then I look at my starting material, what I have. It also helps that, I already have half of A, right? I already have this guy, TSO is a leaving group. So I already have him. He's checked off. I need to make this guy. So in order to make him, notice it's on the carbon right off the ring instead of the carbon 2 off the ring. So I need to move that tosylate. I need to move that oxygen to the other carbon. So what do I need to do? An elimination. In this case, it does not matter what base you use. Well, I guess this is I'm being it would be better to use KOTBU because it's a primary leaving group. Then can I turn this into the alcohol that I wanted?
Can you use the Markovnikov with
It'd
like
have
the
to.
mercury?
Yep, it'd have to be the Markovnikov. Technically, you could use just acidic water here because there's no real threat of rearrangement. But we'll use the fancy stuff. Get more practice writing it down. And then this plus our starting material. With a little bit of base gets us the product. This is just, so someone asked how I did this step. These are just fancy reagents to do the Markovnikov OH addition. You don't need to know how it works. You don't need to know the mechanism. We talked about the mechanism if you're really curious about it, but I'm not going to ask you the mechanism. Um, it's just very convenient reagents to just do an OH Markovnikov and not have to worry about rearrangements. So when I kept saying that it's convenient exactly for something like this, right? If I'm trying to do one of these syntheses, I don't want to have to worry about the OH moving all around, right? And being put on the wrong carbon because then it's going to mess up everything else. So using this is nice. You don't have to worry about rearrangements. It's going to put the OH exactly where you want to put it. Does this, are you guys able to follow this? Okay. Um, there's a lot more practice. This is just getting up to the point of the lecture notes. So you can go back and I would try the lecture notes. So someone asked me about this first step, why we use the bulky base. It's because this is a primary leaving group. So the two times I would use a bulky base is if I'm trying to make the less substituted double bond or when my leaving group is on a primary carbon. It's a primary leaving group. By primary, I mean this carbon has only one other carbon attached to it, as opposed to a secondary or tertiary. So if it's primary, it wants to do substitution, so we've got to use a bulky base to do elimination. Um, yeah, the lecture notes have more practice. The test practice, which I just put out, has more practice. And we'll probably do some more practice on Monday during class. Yes, this is a new skill, but I'm hopeful that honestly practicing it more will also give you more practice with it'll make you feel more comfortable with the reagents, um, which I think will also benefit you for the other parts of the test. So, do you guys have any questions about how these work or um, any sort of specifics of why I'm thinking this? I do think the hardest thing is trying to see this ether disconnection, trying to understand like, hey, I need to make this side and this side separately. One needs to be my nucleophile, one needs to be my electrophile, and then I can put them together. But once you got that down, Then there's a whole bunch of just eliminate, add to get to the correct nucleophile or get to the correct electrophile. All right, do you guys have questions? Are you gonna get 100 on this on the test?
I was just a little confused on like the last problem we did. Um, how you knew instantaneously we had to go to a double bond to get to the right product. Is it just because the OH is like on a different carbon than what the TSO was originally on? Sorry, that was probably really confusing.
No, I
But
know exactly what you're saying. But yes, that's why we did the whole thing at the beginning, right? If I use this TSO and just turned it into an alcohol, and then I did a substitution. So if I did this instead, right? What would my product look like? Do it. See if you can figure out what this product is. Bless you.
Would it just be like the O in the middle with the two benzene rings?
Yeah, it would look like this, right? This would kick off this living group, and I end up with this. Oops. Is this the product that we were going for? No, it's different. It looks different. It has a different name. It's a different molecule entirely. So if we didn't move where this OH was, then we would end up with a different product from our substitution. So planning that out, seeing like, hey, I've got to make this and I've got to make this makes it clearer what we want to do. So this is why people do the retrosynthesis because these big disconnections, like if you just start from the beginning, once it gets kind of more complicated, it can get kind of confusing. I think the eliminations and additions you can kind of see and just do forward. You don't have to do the retro, but seeing that big connection, big disconnection, seeing like, hey, I need my nucleophile to look like this. I need my electrophile to look like this. How can I make my starting materials look like those? Is important, and then you give yourself a goal to work towards. So yes, I did the elimination and the substitution just to move where that oxygen was.
I also have another question. Um, Using the long like HGOAC2, how did we know to use that one? Because is the OH on the more stable carbon or
Yeah, so you could have used H3O plus, um, but like if you wanted to get this, like if we wanted to go back to the oxygen here, H3, we would have to use the anti-Markovnikov version. The big problem with H3O plus is like, say we were working with something that looks like this, and I wanted my alcohol here. If I use H3O plus, I'm risking a rearrangement to get here, which would give me a whole different product, and like it would mess up my synthesis. So yes, it's annoying, all of these reagents, um, but it's more reliable. But honestly, for this is another piece of advice. Let's say you forget that, right? Let's say you forget this whole thing, write H3O plus, like, or let's say you forget something else and like you want to use this, but you forgot what it is. Don't just stop here. Draw the product and then keep going. And then here, just be like, I need the anti-Markovnikov OH. Like if you did that, it'd be like we'd take points off because you didn't know what it was. But like if you took this and then kept going with it, then we'd still give you credit for everything else, right? So don't get stuck if you've forgotten something. Just describe what you want to do and give me the product. Um, it's totally normal. It's totally natural to just forget something, forget exactly what the reagent is, or mess up a reagent, but just keep going, right? Because like there's so much more. Show me the rest of it. I mean, even if you have to be like, you know, question mark, and then like something else that's kind of reasonable off of it, like, yeah, we're gonna take off points because the question mark, but like as long as it's reasonable, the rest of it's reasonable, we'll give you credit for it. Someone said, how can we see the difference between the first ether problems versus these? So I think you mean like these ether problems. So if I go back here, I can still do this disconnection, right? I can still think of it as this. And in this case, like if I look, that OH is on the same carbon as the I, so I don't have to move it around, right? So this one's easy because it's pretty straightforward to make these, right? I made them pretty quickly. I don't have to move the heteroatom from one carbon to another carbon. So I don't have to do the elimination and addition again, right? Take a second, see if you can do the disconnection on the second one. What do we need? Another thing is like these are all symmetrical, right? Like very clearly symmetrical, right? Like that's my disconnection. I can make both of those without having to move this OH. Right? It stays on the same carbon, right? So that's the difference, is that when you plan it, when you do the disconnection, when you see what your goals are, you see, well, like to go from this to this alcohol, I have to change where that heteroatom is, so I have to do an elimination addition to get there. And sometimes, one thing that's not in this worksheet, but that could be on the test or could be on the practice test or could be in the lecture notes is, um, let's do one more problem. I'll try to think of one real quick. See if you can do this one. All right, so there's actually a couple different ways to do this one. You can make the disconnection on either side because both would give you primary leaving groups. So it doesn't matter. So your answer might look a little different than mine, but depending on your disconnection. But if I make my disconnection there just arbitrarily, um, that means that my goals are this and this. Right? So even though I'm not starting with the same starting material twice, I can see how this starting material has to make this product, right? Or this and this starting material has to be from this, or this product has to be from this starting material, right? It seems pretty clear to me. So in this one, how do I get to this alcohol?
HGOAC.
So this makes the less substituted OH. So this is the anti-Markovnikov. So this is going to be the BH3, H2O2, and water. Just a little thing. Anytime you see H2O2, it's going to give you the anti-Markovnikov. No matter what. Like H2O2 and this water will give you the anti-Markovnikov OH. H2O2 Br2 gives you anti-Markovnikov bromine. Or sorry, HBr. So there, I've made this piece. Then I need to move the bromine from one carbon to the other. So I've got to eliminate it. It doesn't matter what I use here. Then again, I need to do the anti-Markovnikov Br addition. So it's HBr H2O2 to give me this. And these two things together, plus sodium hydride, get me that final product.
I had a quick question about the anti-Markovnikov. So, in my original lecture notes, I have BH3 as the first step, and then NaOH and H2O2 as the second step. Did I just copy that down wrong?
That works too. Yeah.
Okay.
Yeah, either way. That's actually probably better. Yeah, I would do that one instead. I probably just wrote this wrong. Um, yeah, so I don't like you don't always use the same material twice. Sometimes you will use the same material twice, sometimes you won't. You can imagine this getting much more complicated. Um, well, it's hard to imagine it being much more complicated with the reactions you guys know, but like it can get more complicated where you use the same starting material twice and then the other starting material once, or some professors in Orgo 2 will say you can use anything, any reagent you can imagine with less than 3 carbons or something. So you might be expected to throw in a random like ethyl iodide or sodium ethoxide or something. Um, I won't do that. I'll just say the only carbons you can use are in the starting materials. Go for it. Let's think. Yeah, I think that's pretty much it, right? This is about as complicated as we can make it, right? I had two different pieces that come together. I had to change the location of the um, heteroatom in both on both pieces before I put them together to do my final substitution. So here we've seen additions, we've seen eliminations, and we've seen uh, substitutions, but now we're using them to make bigger molecules, right? This is the core of synthesis. Can you take these reactions and apply them to do something useful. Um, but again, it's just that next step, right? How well do you know the reactions? How comfortable are you with these transformations, and can we use them to benefit us? And at a certain point, hopefully, it starts to feel a little bit like a puzzle you can uncover. Like, hey, if I do this and this and this, how can I think up of a way to do this to make this product? And as we go on, as these products that we're planning out become more complicated, as you know more reactions, you learn different ways and more ways to kind of approach these issues. And this is going to sound crazy, but like in grad school, like it's a fun thing to do with your organic chemistry buddies, sit around and be like, to look up a really complicated molecule and to see like, hey, how would we try to make this? What are some reactions that we could piece together to make this thing that no one's made before? All right, any other questions? All right, well, I hope this gave you a good starting material to study, do the practice test. We'll talk about it more on Monday. You guys go out, the 12 of you that are still here, and tell your friends how to do synthesis, walk them through it. It will teach you to do it better too. You'll get better at doing it. And if you're watching this on YouTube, thanks for showing up. We will yeah, we'll keep going on Monday, and hopefully you guys can scrounge some points out of this total synthesis on the test, and it's not as scary as it was an hour and a half ago. But thanks for showing up. I'll end the recording now.